Good afternoon to all of you. Welcome you guys. Welcome you all. I hope we are live. So here, could you please confirm whether audio video is clear or not? Please confirm the audio video is clear to everybody. Am I audible to all of you? Chile, let's start our discussions, all of you, everybody. And regarding this Keynote series, in this Keynote series, we are going to discuss about the EMFT. EMFT we are going to discuss, and we are going to cover each and every topics, and briefly I will try to discuss here all the formulas, how to apply the formulas. We'll try to cover it. So continue our discussions, and after completion of the class the complete PDF will be uploaded in the Telegram channel. You can search in the Telegram group, you can search BV Reddy, the Telegram channel. You can search BV Reddy GATE. There you can get my Telegram channel. There I will post this complete PDF after completion of the class. Chalo, let's start our discussions, everybody. Now, and so we have one announcement for you, all of you. So the price is going to hike in Unacademy. So if you want to take the subscription, try to take the subscription as soon as possible before the price going to hike by using a code of BV Reddy. By using a code of BV Reddy, you will get the personalized discount from me and personalized guidance from me. I will take care of your complete preparations. Now these are the top to ESE 2022 rankers from ECA as well as electrical. And there are new batches we are starting for the GATE 2024 for GATE and ESE. So I am starting the digital, I am starting, Shankar sir is starting the signals, right? And these are the batches we are starting. You can have a look at now here, the top educators team you can find here. And these are the USPs of these new batches you can see for GATE 2024. So these are the Udaan batch for GATE 2024. This batch is for all GATE, ESE, IRMS and CSE mains also. You can have a look at the top educators team here. And mission IRMS we have started. Have a look at now here. These are the new batches we are starting. And so this we are conducting, the Unacademy is conducting the combat. The next combat is on 22nd January. With this you will get the real GATE experience आपको मिलेगा. So you can enroll for this mock test by using a invite code of BV Reddy. You can use a code of BV Reddy, so you can utilize these opportunities. It is completely free. And with this we will get the scholarships also आपको मिलेगा. चलो let's start our discussions and we'll discuss each and every point in briefly. We'll cover it. First, सबसे पहले coordinate systems. In coordinate systems, let's talk about the one by one here. So the Cartesian coordinate systems. Can you tell me the parameters in the Cartesian system? What we have? For the parameters in the Cartesian system, we have x comma y comma z, x comma y comma z. And what will be the range of this x, y, z? X can take any values from minus infinite to plus infinite. Y can also take from any value from minus infinite to plus infinite. Z can also take from any value from minus infinite to plus infinite. Right. Now when you are coming to the change in length, so if we see this thing here, now x comma y comma z, The change in length along x direction, how much you tell me? That is a dx. Along y direction is what? dy. Along z direction is what? dz. These are the change in length along x, y and z directions. And coming to unit vectors, what are the unit vectors will take in the Cartesian system? That is ax cap and ay cap and az cap. The angle between these unit vectors are what? 90 degrees. These are perpendicular to each other. Right. This is about the unit vectors Cartesian systems. Next, let's talk about the differential length. Differential length in the Cartesian system. Now tell me the differential length of the Cartesian system, which we used to call this as a dl bar. dl bar, which is given as what we can say, tell me now here. That is dx into ax cap plus dy into ay cap plus dz into az cap. These are the differential length in the Cartesian systems. Now tell me the differential surface areas in the Cartesian system. So xy plane, so change in length along x and y. Change in length along x is a dx, along y is a dy. The direction of surface area is perpendicular to x and y. So what I can say now, this is my az directions. Along yz plane, which is given as dy and dz, and direction is what direction, tell me now here? Ax cap. Zx plane, so which is given as dz and dx, and direction is what direction? Ay cap. These are the differential length. Coming to the differential volumes, tell me now which is given as volume is a scalar quantity. So we need all the three directions are required. So dx, dy, dz. Dx, dy, dz. Done everybody? Next, coming to the cylindrical system. And what are the parameters in the cylindrical system? Cylindrical system, we have the parameters are what? Rho comma phi comma z. Rho comma phi comma z. Next, ranges. What is the range of this rho? Rho is a radius of the cylinder which can be lies between 0 to infinite. And phi is the angle which is given as, tell me now here, 0 to 2 pi. Excuse me. And so z is height of a cylinder. It can take from where to where? Minus infinite to plus infinite. Z is from minus infinite to plus infinite. And coming to the change in length. What a change in length along this rho phi z directions. Rho phi z, change in length. So which is given as what I can say? Change in length along rho direction, which is given as a d rho. Along phi direction, which is given as rho d phi. Along z direction, which is given as what you tell me now, dz. All of you, these are the change in length along rho, phi and z directions. Now, coming to the unit vectors. The unit vectors we can write along this x, y, z directions. Sorry, rho, phi, z directions. What the unit vectors are in the here, which is given as a rho cap and a phi cap and az cap. A rho cap, a phi cap, az cap. And what's the angle between them here? The angle between a rho, a phi, az. How much it is? Which is 90 degrees. Angle between a rho, a phi, az, which is how much? Which is a 90 degrees. Done all of you? एक मिनट. Completed. Now let's talk about differential length. Differential length in the different coordinate systems, you can see here. Now differential length in what system? Now here we are talking here cylindrical system. Tell me the differential length in the cylindrical system here. Which is given as dl and which is given as d rho into a rho cap plus rho d phi into a phi cap plus dz into az cap. Is a differential length in what system? Cylindrical system. Now let's talk about the differential surface area in a rho phi plane. In the rho phi plane, so check it now here. Change in length along rho and phi direction we need to see now, tell me. So which is given as what now here? Rho, d rho and d phi, and direction is what direction you tell me now here? Az directions. And phi z plane is what? Rho, d phi, dz, and direction is what direction? Arrow cap. Perpendicular to phi z plane. Now tell me now here ds, that is dz, d rho, and direction is what direction? Tell me here. This is a phi directions. Coming to the differential volume. Differential volume which is given as rho, d rho, d phi and dz. All change in length we should multiply. Next, coming to the spherical systems. And spherical system, what are the parameters in the spherical system? You tell me. Which are r, theta, phi are the spherical parameters. Tell me the ranges in the spherical system. So the r which lies between 0 to infinite. R is lies between 0 to infinite, and the theta which lies between 0 to pi, and phi which lies between what? 0 to 2 pi. And coming to the change in length, tell me change in length here, that is along r, theta, phi. Tell me change in length along the r direction, tell me, which is given as simply dr. Along theta is what? R d theta. Along phi is what? R sin theta into d phi. And the unit vectors are what we can say now here, that is ar cap, a theta cap, and then a phi cap. These are the unit vectors. And what is the angle between them? Tell me. The angle between them which is what? 90 degrees to each other. Angle between AR, A theta, A phi. How much it is? 90 degrees. So that means what we can say, these are perpendicular to each other. These are perpendicular to each other. Done. Right. Next one. Coming to the differential length in the spherical systems. So which could be given as dl. So here hope all of you are recollecting the things, which is given as what I can say here, dr into ar cap plus r d theta into a theta cap plus r sin theta d phi into a phi cap. Now tell me the differential surface area in which plane here? R theta plane. Surface area in a which plane here? R theta plane, which is given as R dr d theta into what we can say now here? A phi cap. Next tell me now phi theta plane. So here theta, change in length along theta, which is equal to r d theta, and along phi r sin theta. So it will becomes what we can say now here? R square sin theta d theta and d phi, and direction is what direction? Tell me now here? AR. And phi r plane, tell me what we can say now here? R sin theta. So here d phi dr, direction is what? A theta. Direction is A theta directions. Differential volume, tell me the differential volume. We should multiply all the change in length, which is given as what? R square sin theta dr d theta and d phi. R squared sin theta dr d theta and d phi. Done. These are the three coordinate systems we have seen: Cartesian system, cylindrical and spherical system, right? Next, let's talk about the gradients also. The gradient of a scalar function, which we can write del v, and which is the Cartesian system, which is given as, tell me here, which is dou v by dou x into ax cap, dou v by dou y into ay, and dou v by dou z into az cap. This is a gradient in what system here? Cartesian systems. Now we can talk about cylindrical system. Tell me all of you, dv, and which is given as dou v by dou r into ar, sorry, a theta. A cylindrical system now here. First we can write this as dou rho into a rho cap plus 1 by rho into dou v by dou phi into a phi cap plus dou v by dou z into az cap. And which is in what system here? Cylindrical system. Now you can tell me the spherical system here. Spherical system, which is given as dou v by dou r into ar plus 1 by r into dou v by dou theta into a theta plus 1 by r sin theta into dou v by dou phi into a phi cap. This is in a spherical coordinate systems. All of you, I hope all of you are recollecting in the formulas. Everybody? Yes, all of you do like the session and share to the maximum students. Now let's talk about divergence of a vector functions. Let's talk about the divergence of vector function. Next. So if I say A is my vector, divergence of vector, which is given as del dot A bar. Del dot A, which is given as what? Cartesian system, which is given as dou A x by dou x plus dou ay by dou y plus dou az by dou z. Cartesian system. And coming to the cylindrical systems, that is divergence, which is given as 1 by rho dou by dou rho of rho into a rho plus 1 by rho into dou a phi by dou phi plus dou a z by dou z. Then, and this is in the cylindrical system. Coming to spherical system, tell me here. Spherical system. I told you how to remember this thing also. So, which is given as 1 by r square dou by dou r of r square into ar plus 1 by r sin theta into dou by dou theta of sin theta into a theta plus 1 by r sin theta into dou a phi by dou phi. This is in spherical system. Then next, curl. Curl of a vector functions. Now Cartesian system, the curl of a vector which is given as, tell me what we can write now here. Del cross A, which is given as ax, ay, az and dou by dou x, dou by dou y, dou by dou z, and the vector ax component, y component and the z component. This is in what system here? Cartesian system. Next, del cross A, which is in cylindrical system, which is given as 1 by rho into, tell me the unit vectors are a rho cap, rho into a phi, and this is az cap, and which is given as dou by dou rho, dou by dou phi and dou by dou z. And tell me now here which is given as vectors a rho, rho into a phi, and this is az. And the spherical system, del cross A, which is given as 1 by r squared sin theta into what you tell me now here? ar, that is r into a theta, and this is r sin theta into a phi. Right, which is given as, tell me now here, ar, a theta and a phi. That is, we can write, this is what we can say now here, dou by dou r and dou by dou theta and dou by dou phi, and this is r into a theta and r sin theta into a phi. Done all of you? So I hope all of you are recollecting the formulas and all, everybody. Done. Now let's see some of the important things we are going to see now here. Now, yes, tell me now here, if If the divergence of a vector is 0, if the divergence of a vector is 0, then that vector is called as what? If the divergence of vector is 0, then that vector is called as a solenoidal vector. That vector is called as what? Solenoidal, and which is also called as a divergence free vector. Is also called as a divergence free vector, and which is also called as a continuous vector. If the divergence of vector is 0, then that vector is called as a solenoidal, divergence free or continuous vector. Next, if the curl of a vector is 0, if the curl of a vector is 0, then that vector is called as what? Then that vector is called as a irrotational vector. Then that vector is called as irrotational vector or conservative vector. Irrotational or conservative vector. Now, as we know, we have some standard results we have. That is what? The divergence of curl of any vector function, which is equal to what? Always 0. The divergence of curl of any vector function, which is always 0. The next one, the curl of gradient of any scalar function, which is always 0. These two are called as a vector null identities. Right? And yes, as we know the relation, so this is A cross B cross C relation. So triple product, which is given as what? B into A dot C, B into A dot C minus C into A dot B, C into A dot B. Right. Now we can write the relation by combining this thing del cross A bar, which is given as del of del dot A minus del square A. Fine, all of you. These are some of the important results which we use. Right. Next, Stokes theorem. And this Stokes theorem which we use to convert closed line integral to a open surface integral. Closed line integral is converted to a what? Open surface integral. Closed line integral of A dot dl, which is given as what we can say? Open surface integral of del cross A dot ds. By using Stokes theorem, what we can do? We will convert the closed line integral to a open surface integral. Next, divergence theorem. Next one is what? Divergence theorem. By using divergence theorem, we can convert. By using the divergence theorem, we can convert closed surface integral is converted to a volume integral. Closed surface integral, which will convert into a what? Volume integral. So which is given as volume integral of del dot A del dot A into dV. By using Stokes theorem, we will convert the closed line to open surface, and by using divergence theorem, closed surface to a volume integrations. Fine, all of you. Now let's talk about this electric field and magnetic fields. Electric fields, magnetic fields. So the comparison, if you see, so we have the electric field E. In electric field, we have a term called electric field intensity. What is the E is called as a electric field intensity. E is what? Electric field intensity. And the units are volts per meters. Corresponding to electric field, we have a term called H. And what the H is called as a magnetic field intensity. And by using this magnetic field intensity, we can indicate the strength of the magnetic field. This is called as a magnetic field intensity. So with the units of what we can say, amperes per meters. Now in electric field, we have one term that called as a D, where D is called as what? Electric flux density. D is called as a electric flux density, and which is defined as electric flux per area with the units of coulombs per meter square. Coulombs per meter square. And corresponding to magnetic field, we have a term called B, where B, which is called as a magnetic flux density. B, which is called as a magnetic flux density. B is called as a magnetic flux density with the units of Weber per meter square, or we can call it as a Tesla. Weber per meter square or the Tesla. And this D, which is defined as what? So this is a ratio between electric flux per area. Electric flux per surface area. And here the B, which is given as magnetic flux per surface area. Magnetic flux per surface area. Right. Next. And we have a relation between these two. The relation between these two, which is given as, that is D equal to epsilon E. The relation between D and E, D is equal to epsilon E, and corresponding to magnetic field, the relation is B is given as a mu H. B is given as a mu H, and where this epsilon is called as a permittivity of a medium. So this in general epsilon, which is given as epsilon naught into epsilon r. Epsilon naught into epsilon r. Similarly, mu is a permeability of a medium, which is given as mu r into mu naught. And here, so this is epsilon naught is a permittivity of a free space or air, and this value, which is given as 8.854 into 10 power minus 12 farads per meter. And this epsilon r is a relative permittivity, which is always greater than 1. Which is always greater than 1. The minimum value of epsilon r is 1 for in case of air, vacuum, free space. And this mu naught is the permeability of a free space, which is given as 4 pi into 10 power minus 7 Henry per meter. And so this mu r value, which is also greater than 1. And for in case of a non-magnetic material, so mu r will becomes 1. Mu r is 1 for non-magnetic materials. right? And in electric field, the relation if we observe, and here we used to call this as a dipole moment, we can see. In electric field, we can call the term that is called as a dipole moment. Dipole moment P bar, which is given as charge into distance of separations, Q into D, the distance of separations. And so here magnetic field, we have a magnetic moment. Magnetic field, we have a magnetic moment. Magnetic moment, which will denote with a letter of capital M, and which is given as NIA, where N is a number of turns and I is the current and A is the area of cross section. In electric field, we use a term called as a polarizations. Electric field, what we have? Polarizations. The polarizations, so here which is defined as dipole moment. Dipole moment per volume. Dipole moment per volume is defined as a polarization of a dielectric material. And here corresponding to this, here we have a magnetizations. In magnetic field, we have a magnetizations, and which is given as magnetic moment per volume. Which is given as magnetic moment. Magnetic moment per volume is a magnetizations, right? Next, in general, the polarization of a dielectric material, the polarization of dielectric material which is proportional to the electric flux density. So I am using one proportionality constant here, and which is given as chi into D. So this is the polarization of a dielectric material, where this chi, which is called as a electric susceptibility, where so this chi, which is called as what you tell me, this is a electric susceptibility. This is called as a electric susceptibility. And corresponding to magnetic field, so we have a magnetizations, if I call magnetizations, which is directly proportional to the magnetic field intensity H. So we are using a one proportionality constant here, and which is given as mu, which is given as a chi, which is given as a chi m into H, where this chi m, which is called as a magnetic susceptibility, which is called as what? Magnetic susceptibility. Yes. And as of now, we are focusing on the electrical topics. Yes, the common part of EC electrical I am planning to cover. Yes, and based upon your request and all, so here if many other students are requested, then I will do cover the EC topics also I will cover. And chi m, which is called as a magnetic susceptibility. So where this chi m, which is called as what? magnetic susceptibility. Fine, all of you. And in general, so here the electric, so sometimes kabhi time they will give this as a epsilon. So here the relation between epsilon r and chi, which is given as epsilon r, which is given as 1 plus electric susceptibility. Similarly, mu r, which is also given as 1 plus magnetic susceptibility. The relation between electric susceptibility and magnetic susceptibility. Right. Then everybody, यहाँ तक. Yes. So here we can't say na. So here may come. We have a syllabus. We need to discuss it na. It may come. So here. So here, if they want to rare case, you can find. So here, but not all the cases. All the time you may not find. So here, if they want to give this as some tougher things, then they will frame the problem on the susceptibility generally. Done. Now let's talk about this one, electric fields. Now first one is a Coulomb's law. The force between the two charges F, which is given as what we can say here, K Q1 Q2 by R square into AR cap. And with K, what is the K here, which is given as 1 by 4 pi epsilon. If it is a free space, for air, K value given as what? For air is a medium, then the K value, which is equal to 1 by 4 pi epsilon naught, which is given as 9 into 10 power 9. 9 into 10 power 9. 9 into 10 power 9. This is the K value in case of a free space. Done. And we have a different type of current densities as well as charge densities. And we have a different type of current densities as well as charge densities. Now here this is charge densities. And here we will call a royal. What is a royal is called as a, that is line charge densities. Royal is called as what, you tell me? Line charge density. The units are that is coulombs per meters. If we can see the coulombs per meter, that is called as a line charge density. And rho s, which is a surface charge density, which is what? Surface charge density. Rho s is surface charge density. And the units are what? Coulombs per meter square. And this rho v is called as a volume charge density. Rho v is called as a volume charge densities. And mostly we can expect the problems on the volume charge densities. Right, coulombs per meter cube. Next, and Gauss law. According to Gauss law, so the flux is equal to what, you tell me now? Q enclosed. Flux is equal to Q enclosed. Now from this we can see the relation which we have derived. The flux is equal to In general, for closed surface is given closed surface integral of d dot ds, and which is equal to q enclosed, and which is equal to volume integration of rho v into dv. Volume integration of rho v into dv. So by using the second and fourth terms, we'll get the Maxwell's first equation will come now. So which is given as, what you tell me? What will get now? Maxwell's first equation, del dot d which is equal to rho v. Del dot d which is equal to rho v. This is the Maxwell's equation. Right. Next. This Gauss law we have seen. Now, so here we got the Maxwell's first equations and work done. Work done by the electric field. Work done by the electric field, which is given as what? Work done by the electric field W in moving a charge, which is given as Q into integral from A to B. I want to move the body, that is what I can say, E dot dl. Work done by the electric field is given as Q into E dot dl. Now if they are asking to find the work done by the external agent, work done by the external agent, that is opposite to the electric field work. Work done by the external agent, which is given as, what we can say here, minus Q into integral of A to B of what? E dot dl. Generally they will ask to find in the problems work done by the external agent, they will ask, not work done by the electric field. Generally they will ask the work done by the external field, that we are going to, we use a minus sign. And the potential difference, the potential difference which is given as the work done per charge. Work done per unit charge is called as a potential difference, which is given as minus integration of A to B of E dot dl. This is a potential difference between the 2 points A and B. And if the initial point is at infinite distance, then potential difference will become potential. Then the potential is given as work done in bringing the charge from infinite to the finite locations. That is called, here this is a potential difference VAB. This is the potential, which is given as minus integral from, so here some from infinite to some required point of E dot dl is called as a potential. And from this we can get the one Maxwell's equation, that is called as a del cross E, which we will get it as a 0. Del cross E, which is equal to 0. From this, what we can say now here, the curl of the electric field is 0. The curl of a static electric field is 0. So the static electric field is called as a irrotational field. If the curl is 0, which we will call it as irrotational field, I can say now. Call this as a irrotational field. And we will get the relation between electric field and potential. So what is the relation between electric field and potential is given as E equal to what? Minus del V. What is that? E equal to what? Minus del V. This is the relationship between the electric field and the potential, where what is the minus sign indicates, the negative sign indicates that the direction of electric field is opposite to the potential. The direction of electric field is opposite to the potential. That's why we have a negative sign. Then now let's see the electric field and potential for different type of charges. And what are the different type of charges are? Different type of charges: point, line, surface and volume charges. For that we are going to see the electric field and potential, right? Now this electric field intensity for in case of point charges, which is given as what? Kq by r square into ar cap, and potential which is given as kq by r. Potential is given as what? Kq by r. Now you tell me now here, in case of a line charges, the electric field for in case of a line charges, which is given as, that is rho L by 2 pi epsilon into rho into aero cap. Rho L by 2 pi epsilon rho into aero cap. And where what this rho L is? Rho L is a line charge density. Rho L is what? Line charge density. And so as we know, 1 by 4 pi epsilon naught value, how much it is? A 9 into 10 power 9. So if I want 1 by 2 pi epsilon naught value, which is given as 18 into 10 power 9. Right. And then what else you can see now here? Aero is a unit vector. Aero is a unit vector along the rho directions, which is given as what now here? Aero cap, which is given as vector by its magnitude. Rho bar by modulus of rho is a unit vector. It will give the direction of the electric field, where aero cap will give the direction of the electric field. Fine, all of you? All these terms clear? And about the potential, which is given as rho L by 2 pi epsilon into ln of 1 by rho. Ln of 1 by rho. Done? And circular arc. So this electric field for the circular arc, which is given as E, at the center we are finding, which is equal to 1 by 4 pi epsilon into q by r square into sine theta by 2 by theta by 2. This is the electric field due to a circular arc at the center. Consider we have an arc is like this, and this angle is a theta, where r is a radius of this circular arc. We need the electric field at the center. Electric field at the center point, which is given as kq by r square into sine theta by 2 into theta by 2, theta by 2 by theta by 2. And potential formula to same hai. Potential is a scalar quantity, right? So that is 1 by 4 pi epsilon into what? Q by r. Potential 1 by 4 pi epsilon into Q by r. Now coming to this circular ring. Circular ring, consider we have circular ring which is placed in the some plane. either xy plane, yz plane, zx plane. Consider simplicity purpose, we are assuming that circular ring charge which is placed in the xy plane, मान लो xy plane. If it is xy plane, then electric field which is given as rho L A H by epsilon into A square plus H square power 3 by 2. A square plus H square power 3 by 2. If it is placed in the xy plane, the direction of electric field is vertically upwards. If the ring charge is placed in the xy plane, here how the ring charge has been placed you can visualize properly. Assuming the ring charge which I am considering which is placed in the which plane here, xy plane, xy plane. So this is my, assuming this we have, this is my ring. Having this radius we call this as a, and at this point we need the electric field 0 comma 0 comma h, and where h is the distance from center of the ring to this point. H is the distance from center of the ring to this point. Where A is a radius and rho L is what? Charge density. What is rho L is a charge density, coulombs, rho L coulombs per meters. And the potential which is given as rho L A by 2 epsilon into A square plus H square. Potential is a scalar quantity. Potential is a scalar quantity. Now at the center of the ring, center means what we can say, at h value 0 hoga na? At the center of the ring h value 0. So then what is the electric field? You can see electric field is 0, but whereas potential is a maximum value which is given as rho L by 2 epsilon into A. So this is a potential which is a maximum at the center, but whereas electric field is a minimum, right? And I want to find, so we have seen the electric field E which is given as what? Rho L AH by 2 epsilon into A square plus H square power 3 by 2. I want to get the location of the maximum electric field. When it is maximum, now here for that we should differentiate the electric field with respect to H and we will equate it to 0. By simplifying this thing you will get this value. What will get now? H value, the location of the maximum field, which we will get it as H is equal to, that is plus or minus A by root 2. H is equal to plus or minus A by root 2. So at this location my electric field is maximum. A is a radius. Next, surface charge. And the electric field due to surface charge which is given as what? Rho S by 2 epsilon into A n cap. Into A n cap, rho S by 2 epsilon into what? A n cap, where A n cap is a unit normal vector. A n cap is a unit normal vector, normal to the surface charge. Yes, where this A n cap, and this may be positive and it may be negative also. That depends upon the point where you are finding. It is positive if the point lies above. If the point lies above is positive, above the surface charge. and this is negative if the point lies below the surface charge, then it is negative. Fine, all of you. यहाँ तक कोई डाउट हुआ क्या आपको? And for in case of a conducting plate, so the electric field of the conducting plate, which is given as rho s by epsilon, and the unit vector is as it is. In case of a surface charge, rho s by 2 epsilon, but the conducting plate, which is a rho s by epsilon. Next, for in case of volume charges, which we can say hollow conducting sphere, hollow non-conducting sphere, and solid conducting sphere. In all these three cases, the formulas what we are seeing, those are same, right? The electric field for them, which is given as E, which is equal to 0 for in case of a 0 less than or less than capital R. So that means inside the hollow conducting sphere there is no charges will lie, so then electric field is 0, and the electric field we have just on the surface onwards will start. So which is given as, that is 1 by 4 pi epsilon into q by r square. This is for what you tell me now, r greater than or equal to capital R. Now if you draw these variations, now this electric field with respect to distance, how this plot you tell me? This electric field. Now this is the point when small r equal to capital R. Up to capital R, what is the electric field you tell me now? There is no electric field up to capital R. Now suddenly it, when the on the surface of a sphere, so it is rises to a high value, thereafter will decrease like this. At this location, which is 1 by 4 pi epsilon into q by r square. So this is the electric field here. So here inside the conducting sphere there is no electric field. Okay, all of you. Next, coming to the non-conducting sphere. This is most important thing. Now solid non-conducting sphere. Non-conducting sphere means we have a charges inside also. The electric field for in case of solid non-conducting sphere, which is given as R rho v by 3 epsilon into ER cap, and which is also equal to 1 by 4 pi epsilon in q r by rq into AR cap. This is for 0 less than or less than capital R, and that means inside. Outside, the electric field which is given as r cube rho v by 3 epsilon into r square into AR cap, and which is also given as 1 by 4 pi epsilon into q by r square into AR cap. This is the electric field for what you tell me, for small r greater than capital R. All of you. And so if we can see now here how the electric field proportional to distance, you see this thing inside the conducting sphere, electric field E proportional to smaller inside. Inside is directly proportional, you can see. But whereas outside is what you can see now here, 1 by r square, which is outside. Outside is 1 by r square. So if you draw a plot, the variation of electric field with respect to distance, how this plot now here inside, that means up to small r equal to capital R, up to small r equal to capital R, how this variation now here, electric field is directly proportional. It is like a y is equal to mx line now here, straight line here like this, up to where you tell me now here small r equal to capital R. Thereafter it will decreases 1 by r square, like this will decreases. And at this location electric field is maximum. The electric field is maximum on the surface of a non-conducting sphere. Thereafter it will become decrease. Done all of you? Potential you asking? And potential formula, this is electric field. So potential we are talking here. Coming to the potential inside generally, so here the potential formulas are थोड़ा difficult formula, इसीलिए so here mostly I used to avoid the formula. So here अगर आपको चाहिए तो you can do remember these things, and which is given as rho naught by 3 epsilon, so rho naught or rho v, whatever it may we can use. It is rho v by 3 epsilon into 3 r square by 2 minus r square by 2. This is the potential formula inside the sphere. This is the potential formula for inside. And outside formula is simple, r cube rho v by 3 epsilon into r. And this is for outside the sphere. Fine. Inside is rho v by 3 epsilon into 3 r square by 2 minus r square by 2. Outside is r cube rho v by 3 epsilon into r. Now if I want at the center, can you tell me potential at the center of the sphere? Center means what is the radius, small r value 0 now. If I replace small r equal to 0, so what I will get, you see this thing here. What will get a small r value 0, 3 will get cancelled. How much you will get, you can see. How much you will get now? 3 will get cancelled. So which will get exactly, and which is equal to, we can do this thing here. This is rho v, that is rho v r square by 2 epsilon will come now. Now potential of the surface, you tell me. Surface means what we can say, small r equal to capital R. So what will get, you tell me? That is rho v into this is r square by 3 epsilon. You can write now here, if I take the ratio between these two. If you take the ratio between these two, so what will get, you tell me now? V center, the potential at the center, which is equal to what I'll get now here, 3 by 2 times of potential at the surface, you tell me, all of you. Potential at the center, which is equal to 1.5 times the surface potential. Then next, electric dipole. Now, the potential due to the electric dipole V, potential due to the electric dipole V, which is given as what? P cos theta by 4 pi epsilon into r square, where P is a dipole moment, and which we can also write it as vector form as, where P dot AR by 4 pi epsilon into r square. Okay, this is what it is, a potential. And if you want the electric field, as we know, relation between electric field and potential, E equal to what? E equal to minus del V. E equal to what? Minus del V. So from this, what I can say now, electric field E, the relation by applying this formula here, we can get simplifying, that is given as P by 4 pi epsilon into R cube, 2 cos theta into AR plus sin theta into A theta. This is the electric field due to the dipole, electric dipole. This is the electric field due to the electric dipole, where P is what? Dipole moment. P is what? Dipole moment. And theta. So this is what is the dipole moment. We have a, if I say this is my negative charge and this is the positive charge, and so we have the dipole moment is a vector which is along the, from the negative to positive charge, negative to the positive charge. Now here, if we have taken at this point, if we want to find the electric field, let us consider. Now here this point is parallel to this dipole here, isn't it? So this point, which we can call this as a, we used to call this as a end. So here in this case, how much the theta, you tell me, if the point lies here, theta will become, theta is an angle with the dipole moment to the point. So this point parallel, so theta equal to 0. Theta equal to 0. If theta equal to 0, which we can call this as a end fire directions. End fire directions. End fire direction. In case of end fire directions, and you can see now potential here, theta equal to 0, potential will becomes what now here? P by 4 pi epsilon into r square. And the electric field, which is given as, what we can say now, the sin theta value 0, cos theta is 1. So it will becomes what we can say here, 2p by 4 pi epsilon into r cube. End fire directions. Now if I want to find at this point here, this is point is perpendicular, this point is called as broadside directions. So at that location, how much the theta value, tell me. If theta is 90, then we can call this as a broadside directions. Broadside directions. Can you tell me the broadside directions? In case of broadside direction, so potential which is equal to 0 and the electric field which is given as, tell me now here, P by 4 pi epsilon into R cube. This is the broadside directions. Next, Poisson's and Laplace equations. Poisson's equation and the Laplace equation. And what is the Poisson's equation? That is del square V which is equal to 0 is a Poisson's equation. And sorry, del square V which is equal to minus rho V by epsilon is a Poisson's equations. And the Laplace equation is what? Del square V which is equal to 0. This is the Laplace equations. Done. And the capacitance. And the capacitance of we have different type of capacitors. We have parallel plate capacitor, cylindrical capacitor and spherical capacitors. The capacitance of parallel plate capacitor C which is given as what I can say, epsilon A by D. And for cylindrical capacitor which is given as what, 2 pi epsilon L by ln of B by A, where A is the inner radius and B is the outer radius. And the spherical capacitor capacitance which is given as, which is given as, spherical capacitor, so that is 4 pi epsilon by 1 by A minus 1 by B. This is the capacitance of a spherical capacitors. If B equal to infinite, so we can call this as an isolated sphere. We'll call this as what? Isolated sphere. Call this as an isolated sphere. Now the capacitance of an isolated sphere C, which is given as what we can say here, that is 4 pi epsilon A. Capacitance of the isolated sphere which is given as 4 pi epsilon A. Now here in series connections, as we know, series connection, if the capacitors has been connected in series connection, voltage same means electric field same. Electric field same means whatever the current will divide, and charge also will divide. Current will divide, charge also divide. And in case of a series connections, in series connection what happens, you tell me, you can see series connection, current same na, current same means charge also same, but potential will divide na, potential to divide hoga, and electric field lines also divide, electric field also will divide, isn't it? Then next, method of images. So what happens now here, if we place any charge on the surface of a grounded conductor surface, then what happens now, this conductor will induce an image charge. If we place here, this distance is d, then we have image charge now here. This is, we have image charge, this image charge which is equal to minus q, this distance is also 0, then as a result the effect of this outside charge effect is nullified. right? So whatever the electric field lines coming from here, those electric field lines will terminate on the surface of this conductor only. This electric field lines does not enter into the conductor surface. Done? So here if theta is the angle between the two conductors, then the number of image charges which is given as what? 360 by theta minus 1. The number of image charges which is given as what? 360 by theta minus 1. Yeah, equipotential surface. What is meant by equipotential surface means? Hmm? What is meant by equipotential surface means what? Which one here? Where the number of image charges is given as 360 degrees by theta, where theta is the angle between the two conductors. If you have two conductors, the angle between them is theta. Angle between the two conductors is theta, then the number of image charges is given as what? 360 by theta minus 1. Next one. Equipotential surface. Equipotential surface means what? So here on that it is a complete locus where the potential is same. Where the potential is same, that surface is called as a equipotential surface. In the equipotential surface, the work done is zero. Work done, there is no required of potential now here. Work done. What is the work done? Which is given as Q into potential difference. Potential difference is 0, since same potential is same now, then work done will becomes what? 0. And equipotential surfaces never cross each other, means they never intersect. Equipotential surface means same potential. If the two different surfaces are equal, so here then what happens now here? So two different values never be same now, never meet at a point. And equipotential surface is perpendicular to electric field lines. The angle between the electric field and the equipotential surface is 90 degrees. Electric field lines cuts the equipotential surfaces orthogonally. Electric field lines cuts the equipotential surfaces orthogonally. And equipotential surfaces for the so here in case of spheres, so point charges which is a concentric sphere, and for the line charges is a coaxial cylinder. So for the point charges is a concentric spheres, and for line charges is a coaxial cylinders. That all of you? Next, the properties of conductors. The properties of conductors. So here, what are the properties of conductors? You can see now here. What is the electric field inside a conductor? The electric field inside a conductor is always zero. There is no electric field inside a conductor. Electric field inside a conductor is what? Always zero. And what are the net charge inside a conductor? Zero. We don't have any charge lies internally inside the conductor. And conductor does not allow any charge to enter into it. No charge can penetrate into the conductor. And electric field at any point on the surface of a conductor is what? Perpendicular. Electric field is always perpendicular to the conductor surface. Electric field is always perpendicular to the conductor surface. And of course, conductor is a equipotential surface. All of you, conductor is a equipotential surface. Fine. Everybody, all these points are clear to everybody. Next, coming to the magnetic fields. अभी तक हमने इलेक्ट्रिक फील्ड के बारे में डिस्कस किया. नाउ कमिंग टू द मैग्नेटिक फील्ड. And according to magnetic field, potential difference. What potential difference? Potential difference for what? You are asking. The potential difference in a conductor. Oh, that is a problematic analysis now. So here, in conductors, that is a problematic analysis. So here we used to discuss briefly. We'll summarize the things, important things. We'll summarize in these sessions. Okay, those things we have discussed in the class. We have discussed now. That analysis we did in detailed manner. We did the class. We did right. So this Buniyaad's law. Tell me now Buniyaad's law, and which is given as the Buniyaad's law. H. According to Buniyaad's law, H is, that is line integral of I into dl cross r bar by 4 pi r cube amperes per meter. This is a magnetic field. From this we can get the H as what we can say here, line integration of, this is mu naught I into dl cross r bar by 4 pi r cube, and this is a Tesla. Then and Ampere's law. And what is this Ampere's law here? That is closed line integral of H dot dl. H dot dl, which is equal to what? I enclosed. I enclosed. From this we can get one Maxwell's equation, that is del cross H is equal to what we'll get? J. Del cross H is equal to J. From this we can say now the curl of a magnetic field is non-zero. Curl of a magnetic field is equal to current density. All of you? Next, magnetic field due to finite current carrying conductors. What is the magnetic field due to finite current carrying conductor? If we have a conductor, I want to find the magnetic field at this point P. Now what we can do, we'll join this point and this point. Now this current is flowing like this, so I can call this, now here this is my, here this M and N. If I say M is a point, N is a funnel point. Now here if I can call this angle, which is equal to, this is alpha and this angle is beta, alpha and beta. So then the magnetic field H, which is given as what? That is I by 4 pi rho. Rho is a perpendicular distance into what I will get, you can see now here, sine alpha plus sine beta. Sine alpha plus sine beta. And the direction of this magnetic field, which is given as AH cap. AH cap will give us a magnetic field direction, where alpha is the funnel point angle, beta is the initial point angle. Alpha is the funnel point, beta is the initial point. Now if this is a finite length, if alpha equal to beta equal to 90, then it is called as an infinite length conductor. Then this is what? Infinite length conductor. This is an infinite length conductor. For in case of infinite length conductor, the magnetic field H, which is given as what, you tell me? I by 2 pi rho into AH cap. Okay. Now magnetic field due to circular current carrying conductor. Magnetic field due to circular current carrying conductor H. Let us say circular current carrying conductor placed in the XY plane. Consider H, which is given as Ni A square by 2 into A square plus H square power 3 by 2. And the magnetic field is EH cap. I'm indicating we can get the direction of this magnetic field by using right hand thumb rule, all of you. If the thumb is the current directions, fingers will give the direction of the magnetic field. Thumb is a current, curling fingers will give the direction of the magnetic field. Right. Now, this is the magnetic field. Now, if we see this thing here, if H is very high, if H is very much greater than radius, that means very far away, then see this thing, then A value we can neglect now here in this formula. Then the magnetic field, which will becomes what we can say here, if I neglect the A value, so we'll get this as Ni A square by what I can say here, 2 into H cube hoga na, 2 into H cube, isn't it? And this is H. Now from this we can get the B. B is equal to mu naught Nia square by, so this is 2H cube, isn't it? We'll get like that. Done, all of you? Now even if you want to further, you can modify, you can further modify this thing as where Nia is called as what? So here which we can write it as, further we can modify this thing as, which is equal to, this is mu naught by, so this is we are multiplying and dividing with 4, so we can say here 4th pi, mu naught by 4th pi into what I can say now, 2 into Nia, isn't it? Nia square, isn't it? Nia square by H cube, isn't it? We can modify this formula according to requirement, we can do it. Done. And the magnetic field due to a solid cylindrical conductor. Magnetic field due to solid cylindrical conductor. How the solid cylindrical conductor like this now? Is solid one. And so here assuming this is my Z axis and there is a flow of current I which is along the Z directions like this. Now I want the magnetic field inside as well as outside. Now inside the conductor, inside the solid conductor, the magnetic field H, which is given as I rho by 2 pi r square into A phi. This is for 0 less than and rho less than capital R. and which is given as I by 2 pi rho into A phi cap. This is for rho greater than capital R. And you can see now how the magnetic field is proportional to the distance now inside a conductor. Inside a conductor, magnetic field is directly proportional to rho, and this is for inside directly proportional, and outside which is proportional to 1 by rho. This is outside the conductor. So if you draw this variation graph, if you draw how the plot you can see, then how we can see the plot inside the conductor, how the plot inside the conductor and outside the conductor. Inside a conductor is a straight line like this, will increases up to the surface of a conductor, up to small r equal to capital R. Thereafter it will fall down like this. Now, the magnetic field at the center, magnetic field at the center is a maximum, but whereas the magnetic field, and electric field at the center is what? Always 0. For equilateral triangle 0, square 0, and hexagon who 0, circle, for all the cases magnetic field at the center is 0. So electric field is 0, but whereas magnetic field is a maximum, so that magnetic field H, in general magnetic field for in case of n-sided, so which could be given as, that is Ni by pi d into tan 180 by n into sine 180 by n. This is the magnetic field at the center. This is the magnetic field at the center of any figure. If we have considered this where n is an equal sided polygon, magnetic field at the center, which is given as, in case of equilateral triangle, which is given as 9I by 2 pi d. N value 3 na, you can replace, you can get this thing. And for square, so magnetic field at the center, this is one of the very important, try to remember, that is 2 root 2 I by pi d. 2 root 2 I by pi d. Next, hexagon, which is given as root 3 I by pi d. Yes, this recently has been came this form, this one. And for circle, H is given as I by 2r, where r is a radius. Yes, is it visible? Yes, n value tending to infinity now. Right. Done. The next one. The Faraday's laws, the electromagnetic induction. What is the Faraday's law, you tell me? The induced EMF in any closed conducting loop is equal to the time rate of change of its magnetic flux linkage. Is equal to what? Time rate of change of its magnetic flux linkage. The induced EMF. So the induced EMF in a closed loop, which is given as what? Closed line integral of what it is, a E dot dl, which is given as what you can see now here, that is minus of d phi by dt. and that negative sign is according to lens. That negative sign was given by what? Who has given this negative sign? Lens has given the negative sign. And we have where phi is what here? Phi is equal to, which is given as surface integral of B dot ds, and which we can write, if I say area constant, BA into cos theta. Here you can see now the B may be changes, or A may be changes, or theta may be changes. Here you can see the three different parameters. Any one can be changes. So if the B changes, we have a flux changes. If the flux changes, we have EMF. If area changes, we have flux changes. Again we have a EMF. And theta changes, also flux changes. Again we have EMF. Isn't it? So that's why we have three different type of EMFs we have. So those three different type of EMFs we are going to see here. Now if B is a function of time, if the magnetic field changes, if the magnetic field changes with time, then we can call that EMF is called as a statically induced EMF. We'll call that EMF as what? Statically induced EMF, which is given as EMF is given as surface integral of B dot ds. Okay. And so here if the effective area changes, then we can call them as a dynamically induced EMF. And the effective area means here this A effective area means the A cos theta is called as the effective area. So here if A changes, we have effective area changes, and theta changes, also effective area changes now. So this term is called as a dynamically induced EMF. Then this EMF which is given as, if the conductor, if the area changes, we can call this as a motional EMF. If area changes, we can call that as a motional EMF. And if the theta changes, we can call that as a rotational EMF. What is the motional EMF? So which is given as line integral of V cross B dot dl. This is a motional EMF. And the rotational EMF is what? NBA omega into sine theta. Theta changes, magnetic field is constant, area constant, but the loop is rotating. Then we can call that as a rotational EMF. The rotational EMF which is given as NBA omega into sine theta. Okay. NBA omega into sine theta. These are the EMF. Next, Lenz law. Coming to the Lenz law. What is the purpose of this Lenz law? To find the direction of the induced current. To find the direction of the induced current, we use a Lenz law. And this we use to find the direction of induced current if it is a closed loop only. Closed conducting loop only, we can apply the Lenz law. And this Lenz law, which is based upon the law of conservation of energy, and which is a consequence of Newton's law. And what the Lenz law? It states that current flows in a closed conducting loop in such a direction that it tries to oppose the cause which is producing it. Yes, so this thing you can see now, current ऐसे बहता है कि उसी का नष्ट करना चाहता है जिसने उसको फायदा किया. Isn't it? So it will opposes the cause producing it. So there is an induced current in the loop in such a manner it opposes the cause producing it. It opposes the cause producing it. Isn't it? That is a Lenz law. Done all of you? and this is the consequence of Newton's third law. Then, so this is up to the electrical syllabus. And regarding this ECE topics now here, and so you do message me, so then we can plan one day, we can plan exclusively for remaining topics of ECE. Okay, yeah, that's for the today's sessions, and we'll meet tomorrow same timing. We have control systems, we have tomorrow same timing, we have control system, and we'll meet in the control system same timings we have. Okay, then see you, bye.